Hello, everyone. We're going to go ahead and go over section 4.4, which is on the laws of logarithms today. So we've learned about logarithms in our last section, 4.3, and now we're going to go over some really helpful laws that we'll have in order to simplify logarithmic expressions or expand logarithmic expressions. So there we go. Now that we've learned about logarithms, we can have some helpful properties that will give us a wider range of applications with logarithms. So since logarithms are technically exponents just rewritten, we can actually modify the law of exponents to give us the laws of logarithms. So the laws of exponents, you can always feel free to look those up. That is when you multiply two terms with the same base with different exponents, you add their exponents. If you divide two terms with the same base with different exponents, you would subtract the exponents. If you raise an exponent to the power of another exponent, you get to multiply those exponents. So those are the laws of exponents, just a very brief overview. Once again, you can always look those up if you don't quite remember those. But we can modify those to give us the laws of logarithms. So the laws of logarithms will work very similarly. We will take, terms that have logarithms in them and maybe they're being divided, we can separate that into the subtraction of logarithms. Or if we have a logarithms where two things are being added, we can turn that into, or two things are being multiplied, we can turn that into the addition of two logarithms. Or if you have a logarithm of something with an exponent, you can turn that into the multiplication of two logarithms. So these are going to be the laws of logarithms. Just once again, brief overview. We will see them in the upcoming slide. But this will allow us to add, subtract, multiply, divide, and raise logarithms to a power. So in our image here, we have a log in the form of a clock, and every logarithm term there is the numbers on the clock. So, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, back to 12. So it is the log clock of logs. Haha. All right. Here we go. Laws of logarithms. So here are the laws of logarithms. We have some logarithms here. We say that a is a positive number and it's not equal to 1. We would let capital A, B, and C be any real numbers where A and B both have to be positive. So one note is that C does not have to be positive. We will see that for the third law of logarithms. All right, so for the first law of logarithms, we have log sub base lowercase a, so log of some base, of capital A times capital B can be separated into log base lowercase a of capital A plus log base A of capital B. So if two numbers are being multiplied within the logarithm, you can break them up into two completely separate logarithms with the same base. And this does work in either direction. If you have log base lowercase a of capital A plus log base lowercase a of capital B, you can turn that into multiplication as well. So they work both ways. If you have one, you can turn it into the other. So this is the logarithm of a product. It's really going to be the sum of the logarithms. And very similarly for logarithm 2, or the law of logarithms 2, we have log base lowercase a of capital A divided by capital B is equal to log base lowercase a of capital A minus log base lowercase a of capital B. So very similar to the first law of logarithms. It's just division and subtraction instead of multiplication and addition now instead. So this is the logarithm of a quotient is the difference of the logarithms. And just like laws of logarithms number 1 with addition and multiplication, this also works in both directions. If you have one, you can turn it into the other. This one, you can turn it into that one. So we see that they can be used interchangeably based on kind of the context of a problem. All right, then our third law of logarithms here, we've got log base lowercase a of capital A to the power of C. Now, note at this point, A and B always have to be positive, but C does not necessarily have to be positive. C can be negative as well, or it could be 0. So we have log base A of capital A to the power of capital C is equal to C times log base A of capital A. So if something is raised to an exponent, you can take that exponent and bring it out to become a coefficient of the logarithm. So that's how we would rewrite that. So we say the logarithm of a power of a number is the exponent times the logarithm of that number. So this is the way, once again, interchangeable. You can, use one to get to the other, use this one to get to that one. Either way, in the context of the problem, whichever one that you would need. So these are the laws of logarithms and how to expand and combine logarithmic terms. So for example 1, we're just going to evaluate each expression. For part A, we have log base 4 of 2 plus log base 4 of 32. For B, we have log base 2 of 80 minus log base 2 of 5. And C, we have negative 1/3 log of 8. So we're going to go ahead and we're going to do these problems in our notes. All right, so here we are in our notes. We've got our problem 1, and let's go ahead and start with part A. So log base 4 of 2 plus log base 4 of 32 is equal to what? So in order to combine these two logarithms to just have one single logarithmic term, we can use one of our laws of logarithms. And the one we'll want is the first one. So we would want the first law of logarithms, LOL. So we're going to use the first law of logarithms. It is log of lowercase a of capital A plus log of lowercase a of capital B can be simplified into log base lowercase a of a times b. So that's the first law of logarithm. That's the one that we're going to use in this case, which means that we're going to have log base a, where we see both logarithms as log base 4. So this will turn into log base 4 of, and now we take the numbers that we were taking the logarithms of. So 2 and 32 will now be multiplied. So 2 times 32, like that. So we have log base 4 of 2 times 32, which 2 times 32 is 64. So we have log base 4 of 64. Once we're at this point, whether or not you want to plug this in a calculator, or if you know what the answer would be, then excellent. But remember, since this is a logarithm, it's the rewriting of an exponential problem. So log base 4 of 64, we are saying that this is equal to something. It's equal to, let's say, or yeah, we can say that. So we know that this is equal to some, letter y or x, or whatever term that you would like to say. Let's go ahead and say x is equal to x. So if you have log base 4 of 64, this is essentially saying that we have the base of our exponent is the base of the logarithm. So 4, and the answer or the result is 64, and x is the exponent. So this would be 4 to some power of x is equal to 64. That is what the logarithm is really saying in an exponential form. So sometimes it's easier to take your logarithm and express it in its exponential form to kind of get a better idea of what you should be doing for the problem. So log base 4 of 64 is the same thing as saying 4 to some power is 64, and the answer is going to be x. So we could go to our calculators, do 4 to the power of 1, 4 to the power of 2, 4 to the power of 3, and we would get that that was the answer. So you could test out a couple powers of 4 to see what you get as the answer of 64, which we would get 3. So this would be our answer here for log base 2 of 2 plus log base 4 of 32. Our answer would end up being equal to 3. All right, then for part B, we have log base 2 of 80 plus log base 2 of 5 is equal to what? So for part B, we are going to use the second law of logarithms. Second LOL. And the second law of logarithms tells us that log base lowercase a of, we'll go in the backward direction here, of capital A minus log base lowercase a of capital B is log base a of capital A divided by capital B. Which is, I just realized I had a little bit of a typo. That was supposed to be a minus from the original slide that we had before. So that is a minus. We will be using the second law of logarithms. That was my mistake there. So we are going to use the second law of logarithms. We do have a subtraction, as we just edited it to and corrected that. So now we are going to write it in its more combined form. So it's single logarithmic term. So in this case, we have log base 2. So that lowercase a is 2. So we have log base 2. And then we're going to have capital A divided by capital B. So we take the first number from the first logarithm, that result that you're actually taking the logarithm of. So 80, you're going to take 80 divided by 5, the number that you were taking the logarithm in the second one. So this is 80 over 5. And now we can simplify. 80 divided by 5. Whether or not we put that into a calculator, brains, we get that is equal to 16. So we would have log base 2 of 16. We want to know what this is equal to. And just like last time, we could say this is going to be equal to some number x, where our logarithm base 2 of 16 is the same thing as saying 2 to the power of x is equal to 16. That same power of x is going to be our answer. So we go to our calculators. If you know it already, excellent. If you don't, you can go to your calculator, do 2 to the power of 1, to the power of 2, to the power of 3, to the power of 4, and we would get that 2 to the power of 4 is equal to 16. So our answer for this question would be 4. All right, then lastly, part C, we have negative 1/3 log of 8. So for this problem, we have a coefficient in front of a logarithm. So that coefficient is going to indicate that third law of logarithms. That's the only way that you have a coefficient with the laws of logarithms. So we have the third law of logarithms here. So the third law of logarithms tells us that if we have some number c times log base a of capital A, then this is the same thing as having log base lowercase a of capital A to the power of capital C. So what we have here is that first form with the coefficient outside the logarithm. So we're going to rewrite it with our laws of logarithms. When we rewrite it, we're going to have our log, and we have log base a, and we don't have necessarily an indicated logarithm for part C. It just says log. So remember, if it just says log, it really means log base 10. So even though we're just writing log, it's really log base 10. We want to remember that that's what that means. So we've got a little 10 right here in our brains. We're going to erase these now because the 10s are in our heads. We know it means the logarithm of base 10. So we have log of base 10 is going to be equal to capital A, which is the number that you're taking the logarithm of. So this is 8 to the power of negative 1/3. That's the value of C. So this will be 8 to the power of negative 1/3. Let's make that a little bigger. There we go. So we have logarithm of 8 to the power of negative 1/3. Now you could plug this into your calculator almost immediately at this point, and you could find this value. Or you could mess around with it a little bit. We see 8 to the power of negative 1/3. A negative exponent could be the same thing as 1 over that same exponential expression, just with a positive exponent. So for example, 8 to the power of negative 1/3 is the same thing as 1 over 8 to the power of 1/3. So instead of negative, you would have a positive number, and you put 1 in a numerator. So we can go ahead and rewrite that. We get log of 1 over 8 to the power of 1/3. All right, so we have log of 1 over 8 to the power of 1/3. The power of 1/3 also indicates a root problem instead of an exponent. Well, it's still an exponent, but you can rewrite it as a root instead. So, as a reminder, let's pick a better green color, actually, a little darker. There we go. So, as a reminder, some number to the power of a fraction would be a root problem. So like a to the power of 1 over b is the same thing as the b root of a. And 2 would indicate a square root, 3 indicates a cubic root. So this is also the same thing as saying log of 1 over the cube root of 8. So the cube root of 8, it would be 2 to what number equals 8. So a little bit there of kind of that rewriting. Or you could use your calculator to find the cubic root of 8. You'd want to know 2 to the power of what number equals 8. And the answer is going to be 2. So the cubic root of 8 is 2. So 2 to the power of 3 is equal to 8. So, all right, so we have that the cubic root of 8 is going to be 2. So this is really log of 1/2. Now you want to evaluate this expression. So what we're going to do is we're going to put log base 10 1/2 in our calculators. So you can go ahead and put that in your calculator now. You can go ahead and take a second to do that. And our answer will be about negative 0.30103. Just barely squeeze that in there. And that is our answer there for part C. So for part C, we used quite a few different types of kind of exponential properties in there. So it was quite the mixture of things, which is another common thing that you may see when like doing things like your homework. You may see that, you use other properties like exponential properties and things like that in order to do your problem. There's always the option of course, putting something straight in from the get-go. You could put log base 10 of a to the power of negative 1/3 into your calculator from the get-go and get the same exact answer. Or you could try to rewrite it in the way that we did to also get the same answer. It would be completely up to you. So, all right, that finishes up problem 1. So let's go ahead and go back to our lecture. All right, so that was example 1. So moving on to expanding and combining logarithmic expressions. So the law of logarithms allows us to write the logarithm of a product or a quotient as the sum or the difference of logarithms. And this is the expanding of a logarithmic expression. Essentially, taking something that is one logarithmic term and making it bigger is expanding. So taking that multiplication or division and turning it into addition or subtraction is expanding a logarithmic expression. This also includes taking an exponent and making it into a coefficient as well. That is also expanding. So remember, expanding is always taking something smaller and more compact and spreading it out into kind of all of its individual terms. So expanding, just the word in general, expanding means to get bigger. So you are taking a compact logarithm and expanding it into all of its single logarithmic terms into sums or differences or coefficients. So that's what expanding a logarithmic expression means. So if you're asked to expand a logarithmic expression, that is what it wants you to do. Then we have the law of logarithms also allows us to reverse that process of expanding. And we could write the sums and the differences of logarithms as a single logarithmic term, a multiplication or division, or with exponents. And this is called combining. So combining is taking multiple things and all kind of shoving it into one thing. So you're taking multiple logarithmic expressions and putting them into one single logarithmic expression, which is what combining a logarithmic expression is. So we have expanding and combining logarithmic expressions, both cases. So if you're asked to do one, if you're asked to expand, you need to spread out your logarithm. Take what is pretty much singular and make it multiple terms. With combining, you're taking something that has multiple logarithmic terms and you turn it into one logarithmic term. So that's what those words mean when you're asked for them on your homework. You want to look at a little bit of a hint as well when it gives you the problem. If it gives you the problem and it's one single logarithmic term, it probably wants you to expand. If it gives you the problem and it has multiple logarithmic terms, probably wants you to combine. All right, so saying that, lastly, we do have a warning. So although the laws of logarithms tell us how to compute the logarithm of a product or a quotient, there is no rule for a logarithm of a sum or a difference. So for example, something like this example down here, log base lowercase a of x plus y is not the same thing as log base a of x plus log base a of y. We saw that log base a of x plus log base a of y corresponded to log base a of x times y. So you have the laws of logarithms and they're very helpful. They can be used in many different ways, but you cannot extend that knowledge. The laws have to be exact. You can't say, oh, okay, well, that looks close enough, so I'm just going to use the law of logarithms. You cannot do that. So you need to, remember, have written down on your note card, I think, for an exam, like have the laws of logarithms very explicit because they are not always the same. You can't just use them whenever. So same thing goes for log of 6 divided by log of 2. That is not the same as log of 6 over 2. This statement here, log of 6 over 2, would be equal to log of 6 minus log of 2, not log of 6 divided by log of 2. The values are not the same. So you cannot use laws of logarithms in cases like this. Same thing goes for log base 2 of x, all of that to the power of 3. The exponent needs to be inside the term that you're taking the logarithm of, not on the outside. Because this would not be the same thing as 3 times log base 2 of x. The exponent was not being applied to just x. It was being applied to the entire logarithm. So this is also not the same. So you cannot improperly oversimplify or just improperly simplify in general. The laws of logarithms are very, they're pretty straightforward, but they're also very strict. You cannot just kind of fiddle around with it and think that, oh, these are similar, I can do this or that. No, it has to look exactly like the laws of logarithms in order to use them. So you do have to be careful about those things. Things like on the homework, it will try to trick you and think that you can do one of these when maybe you can't. So it's just a good thing to keep in mind when you can and when you cannot use a law of logarithms. So, all right, moving on to example 2. We're going to use a law of logarithms. 2a, we're going to expand log base 5 of x cubed times y to the power of 6. And we are going to combine 3 times the natural log of s plus 1/2 natural log of t minus 4 times the natural log of t squared plus 1. So let's go ahead and go on over to our notes so we can work this problem out. All right, so example 2, part A, we're going to expand log base 5 of x to the power of 3 times y to the power of 6. So when we expand this, we always want to go with the easiest kind of steps first, the most clear-cut steps. So if we look at this, we see that the x term and the y term are being multiplied. So we can use the first law of logarithms to separate it. Now, if you looked at this and first went, oh, there are exponents, I'm going to bring the exponents to coefficients. The issue that you would run into is that the exponents are not the same. And since they're not the same, they'd have different values. You'd have to bring out the exponent, you'd still have to separate them, and then you'd have to do it again. So you could definitely still do it, but it would take extra steps. So instead, we will just start with separating the x and the y terms. Since they're being multiplied together, that tells us we can use the first law of logarithms. So to separate, we'll use the first law of logarithms, which means that we will turn this into the sum of 2 logarithms. So we'll separate them out. This will turn into log base 5 of x to the power of 3 plus log base 5 of y to the power of 6. So that's our first step there. Let's actually bring this down to the next line. So we have our two logarithms. They have been separated. When you're expanding or combining terms for logarithms, you always want to make it into the most combined or the most expanded. Since we're expanding, we want this to be expanded as much as we possibly can. So we do still have those exponents left. So we want to get rid of the exponents. So we're going to go ahead, and because of these, we're going to use the third law of logarithms. The third law of logarithms will allow us to take those exponents and turn them into coefficients. So taking them into coefficients, you'll take that 3, move it out to the front, take the 6, move it out to the front. We'll end up with 3 times log base 5 of x plus 6 times log base 5 of y. And looking at our two logarithmic terms, we see there's no more multiplication within the logarithm, there is no more division inside the logarithm, and there are no more exponents inside the logarithm, which means that we have successfully expanded our answer as much as we possibly could. So that would be our answer for part A. So when you're expanding, when you get to your final answer, or it should indicate that you've gotten to your final answer when there's no more multiplication, division, or exponents within the logarithm. The coefficient does not count. It would be kind of outside the logarithm. We're talking about within those parentheses of the actual logarithm. That's where you do not want multiplication, division, or exponents. Since we don't have multiplication, division, or exponents inside those logarithms, then we're good, and that would be our answer. So, all right, now we move on to part B. Part B, we're going to combine our terms here, 3 times the natural log of s plus 1/2 times the natural log of t minus 4 times the natural log of t squared plus 1. So we want to combine this, which means that our term that we're given here has addition, subtraction, coefficients. We want to bring all of this into one single logarithmic term. So we're going to take our coefficients, turn them into exponents. We're going to take our sums, turn it into multiplication. And we're going to take our division and turn it into, or our subtraction here and turn it into division. We need to do all of these things. But we need to figure out what's kind of the order that this needs to go in. And the answer is that you can probably go in almost any order. As long as you're very clear about what you're doing and keeping everything kind of in line, you could go in any order. The same goes for part A as well. You could have gone in a different order, it just might have led to more steps. In my opinion, it's always best to get rid of coefficients or exponents first and then deal with the multiplication or division. If we actually think about the order of operations just in general, that PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, then we see that, exponents comes above multiplication or division. And also here, multiplication comes before addition or subtraction. So if you follow the order of operations, that can actually lead you most likely into kind of the shortest steps and the fastest answer. So you can follow the order of operations if you kind of want a rule of thumb, but you can remember you can still go in any order, it just may not be as efficient. So, all right, saying all that, we're going to go ahead, we're going to start with the third law of logarithms. So, wrong one. We're going to take this 3, 1/2, and the 4, and we're going to make those all the third law of logarithms. So we're going to bring them all into exponents. So we're going to turn ln, or 3 times ln of s. This will be the natural log of s to the power of 3. So we're going kind of in that opposite direction. We're taking those coefficients and turning them into exponents. Then we've got plus the natural log of t to the power of 1/2 minus, and we have 4 times the natural log of t squared plus 1. We notice that t squared plus 1 is what is inside the logarithm. So the 4 would be the exponent of whatever's inside the logarithm. And if you're thinking to yourself, oh, natural log of t squared plus 1, well, I could expand that because it's addition. You could, but remember we're combining. So it'd be very counterintuitive to do that. So since we're combining, we're going to leave t squared plus 1 by itself. We're going to bring that 4, and it's going to be the exponent of t squared plus 1. So this will be minus the natural log of t squared plus 1 to the power of 4. So that exponent went into the entire expression inside the logarithm. So, all right, we use the third law of logarithms. We turned all of our coefficients into exponents. And now what we have left over is addition and subtraction. At this point, it genuinely doesn't matter kind of which one you pick. We know that in order of operations, multiplication and division and addition and subtraction are both on the same level. It's just that, to create the word PEMDAS, it worked better to have the M in front of the D and the A in front of the S. But so we can go in any order. I always just recommend going from start to finish. So if we read this problem in order from like left to right, the addition comes first. So we can do that one first. So, all right. Since the addition comes first, this right here indicates to us the first law of logarithms. And in addition to that, it's just the first 2 terms. So we're going to use the first law of logarithms on just the first 2 terms. So when we use our first law of logarithms, we're going to take what's inside the logarithms and multiply them together to get rid of the addition sign. So this will be the natural log of s cubed times t to the power of 1/2. So we combine the first 2 terms, and we still have the last one there. We're still subtracting the natural log of t squared plus 1 to the power of 4. So now what's left over is the only law of logarithms that we really have left, which is the second law of logarithms. So with that second law of logarithms, we're going to take what's in the logarithm of the first term and divide by what's inside the logarithm of the second. So we're going to have ln of s cubed t to the power of 1/2 divided by t to the power of 4 plus 1, or sorry, that was to the power of 2. T to the power of 2 plus 1, all to the power of 4. And we have the logarithm of that entire thing. And that would be our answer. Now, if you wanted to simplify anything at all, you could turn the t to the power of 1/2 into the square root of t, but either way, it is still correct. You don't have to write square root t if you already have t to the power of 1/2. And you absolutely do not need to simplify t squared plus 1 to the power of 4. Since it is an exponent and there are 2 terms in that exponent, you do not get to distribute the 4 as an exponent. It would be t squared plus 1 times t squared plus 1 times t squared plus 1 times t squared plus 1, which would just be a monster to try to multiply out, and you do not have to do that. As a rule of thumb, if it's easy to simplify, you definitely want to simplify. If it's not going to be easy to simplify, you probably don't have to. So you do not have to simplify t squared plus 1 to the power of 4 because it would be very long and very tedious. But you could write square root of t instead of t to the power of 1/2 if you wanted, but they are both correct. So, all right, looking over our answers there, that was problem 2, easy sum laws of logarithms. We looked at how to expand and how to combine logarithmic terms. So, all right, let's go ahead and go on back over to our notes. All right, so that was example 2. Now we have the change of base formula. So in some instances, it's very useful to change the base of a logarithm to another base, especially if you want to use a calculator to compute the logarithm. Now, a lot of newer calculators can actually calculate the logarithm of any kind of base, and I will leave that up to you to figure out how to do that if you would like to do that. But a lot of calculators, including the calculators provided most likely from schools, will not have that formula in it. And so in that case, you would have to use the change of base formula. So for any base lowercase b, if you have log base lowercase b of x, then you could express that logarithm of logarithm base lowercase a of x divided by log base lowercase a of b, where a is commonly going to be base 10 or e. This is going to be the common or the natural logarithm, but it can really be any value. It can be any value that you would like. If it's going to be very, simple, if you pick log base 2, then that's great. Or if it's going to be a difficult one, you could definitely pick log base 10 or log base e, which is in your calculator already. So that would be just the common logarithm or the natural logarithm. So it makes it so that it's fairly easy to still calculate in your calculator without picking a different base that is going to still kind of create it into an algebraic problem. You could compute it just straight with your calculator. And it doesn't matter which one you pick, common logarithm or natural logarithm. The answer will still be the same. You just need to make sure that it's matching. You just need to make sure that you don't use a common logarithm in the numerator and a natural logarithm in the denominator. It just needs to be the same. It needs to be common logarithm divided by common logarithm or natural logarithm divided by natural logarithm. But we see that the value that we took the logarithm of goes to the value in the numerator, and the base of the logarithm goes to be the logarithm of the denominator, the value of the logarithm of the denominator. So we kind of see those numbers kind of switch there, and then you get to pick what A is. Very commonly, it's going to be 10 or E. So, all right, that is a change of base formula. Let's go ahead and try it out. Example 3, we're going to use the change of base formula and the common or natural logarithm to evaluate the expression rounded to 5 decimal places. We have log base 9 of 20. So instead of going to our notes, we're going to use our online calculator. It is a TI-84, just in digital format. So if you have a TI-84, that's great. That's full match very well. If you have a different type of calculator, then you'll probably just have to find these values on your calculator. But all right, let's go ahead and try this out. This is log base 9 of 20. All right, we have log base 9 of 20. And with our change of base formula, this would turn into log, if we use the common logarithm, it would be log of 20 divided by the log of 9. So we're going to go ahead and plug that in. So we'd have log of 20 divided by log of 9. We press enter, and this is our answer, 1.363416514. We can do the same thing with the natural logarithm. So this would be the natural logarithm of 20 divided by the natural logarithm of 9. And we see we got the exact same answer. So you will get the exact same answer whether or not you use logarithms or the natural logarithms. But that would be how we would do it. The value of the logarithm comes first. The undesirable base that you had would come second. So that would be the one in the denominator. So we're going to go ahead. We're just going to write this in our notes. We're kind of expanding out into the change of base, log base 9 of 20. But we know what the value is going to be now. So let's go ahead and just write our answers in our notes. All right, so we had log base 9 of 20. Our change of base formula is log base b of x is equal to log base a of x divided by log base a of b. So in our case, we could pick, log base 10 to start off with, which is just the common logarithm, so we would just write log instead. And we see that this 20 comes up here, and the 9 goes down below. So we had that log base 20 divided by log of 9, log of 20 divided by log of 9. And using our calculators, we said this came out to 1.363 4, and rounding to 5 decimal places would come out to 2. So 1.36342. And like we showed on the calculator, it does not have to be the common logarithm. It could be the natural logarithm as well. So this would be the same thing as the natural log of 20 divided by the natural log of 9, which comes out to the same answer, 1.36342. So either one you pick, common or natural logarithm, it will work out the exact same way when you use the change of base formula. So, all right, let's go on over back to our lecture. All right, so that was example 3, and that finishes up our section. So in section 4.4, we learned about the laws of logarithms, expanding and combining logarithms, and the change of base formula. So, all right, that wrapped up our section, and I'll see you in the next one.